In the diagram below, a small metal sphere A on an insulating rod has a charge of minus 80 times 10 to the power minus 9 coulombs. And then 7.1 says, describe the term electric field in words, right? An electric field is a region of space in which an electric charge experiences a force. A region in space in which an electric charge experiences a force. Basically, we're saying that E is equals to F divided by Q, right? That's the formula for electric field. A region in space where an electric charge will experience a force. And then 7.2 says, calculate the number of electrons sphere A has in excess, right? So the number of electrons a sphere will have in excess will be equals to its charge divided by the charge of an electron, assuming it has a negative charge, right? Because if it has a positive charge, then it doesn't have any electrons in excess. In this instance, we're going to have minus 80 multiplied by 10 to the minus 9 divided by the charge of an electron, which is minus 1.6 times 10 to the minus 19. So I'm getting 5 times 10 to the 11 electrons. So this sphere has 5 times 10 to the 11 electrons in excess. And then we are told now that sphere A is now kept vertically above another sphere B of mass 0.01 kg lying on a horizontal insulated surface. The charge on sphere B is plus 120 times 10 to the minus 9. Sphere A is closely brought closer to sphere B in order to pick it up. Ignore the effects of friction. Okay, and then 7.3 says that draw a diagram that shows the electric field pattern between spheres A and B. So sphere A is negative, let's put it here, and then down here let's have sphere B, which is positive. So the electric field on sphere B, which is positive, will be pointing out, while the electric field on sphere A, which is negative, will be pointing towards itself, right? So let's have something like that. So for sphere A, the electric fields are pointing towards it, and then for sphere B, the electric fields are pointing out, right? And sphere A and B will attract each other. So let's demonstrate that using our electric field lines, right? Yeah, so at the end of the day, you're going to get something like this. If you want to be more precise, sphere B has a greater magnitude compared to sphere A. So you can put more electric field lines pointing out of sphere B, since it has a greater magnitude. And then 7.4 says at a certain height h, sphere B is just lifted off the surface due to its attraction to sphere A. Just lifted off, right? Let's note that, just lifted off. And then draw a free body diagram showing all the forces acting on sphere B at this instance. So let's talk about the keyword just in this statement line. So if it is just lifted off, then that tells us that the force that is lifting it off and the force that are keeping it down, they are very, 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 very close to each other. They are approximately equal. So that's why it is just lifted off for a split of a second, right? So let's look at sphere B and do some analysis. So if sphere B is being lifted off, it's going to be lifted off by the attraction from sphere A, right? So let's have an arrow pointing up here and demonstrate that this is FA on B, and then what's keeping it down is gravity, right? Because it is said to have a mass of 0.01 kg. So let's have Fg here. So we need these two lines to be approximately equal to each other because the sphere was just lifted off. And then 7.5 says calculate the height h in the diagram at this instance, right? So we definitely gonna use the free body diagram of sphere B, right? Because that's the only information we have. So we're gonna say that FA on B is equals to FG. So FA on B will be K Q1 Q2 divided by R squared, and Fg will be the mass multiplied by the gravity. So what is the value of K? We know fully well that K is 9 times 10 to the 9. The charge on Q1, let's say Q1 is A, that will be 80 multiplied by 10 to the minus 9. Don't forget, we are only interested on the magnitude of the charges and not the direction. And then for B, we're going to have 120 times 10 to the minus 9. And then we divide everything by R squared. So R in this instance is H, right? So we're going to have H squared, which is equals to the mass 0.01. Gravity is 9,8, right? So now we're basically solving for H squared. So if we cross multiply, H squared is going to be multiplied with 0.01 multiplied by 9,8, right? And then we're going to end up dividing both sides by 0.01 multiplied by 9,8. So we're going to have H squared being equals to 9 times 10 to the 9 multiplied by 80 times 10 to the minus 9 multiplied by 120 times 10 to the minus 9. And then this we are going to divide it by 0.01 multiplied by 9,8. So now we can take square roots on both sides, right? So we will say h squared to the power 1 divided by 2 is equals to this entire expression to the power 1 divided by 2. So h will be equals to 0.0297 meters, right? And then let's move to 7.6. And now we are told that sphere A is now placed on the horizontal insulated surface a distance x from sphere B as shown in the diagram below. P is a point between A and B, which is 0.05 meters from B. The magnitude of the net electric field intensity at point P as a result of the presence of sphere A and B is 54.45 times 10 to the 4 nano per coulomb. And then 7.6 say draw a labeled vector diagram indicating the directions of the electric field at point P as a result of spheres A and B. So point P is a point charge, right? So we always assume that it's positive. And then sphere B is positive, right? And then sphere A is negative. So how do point P and sphere B interact? They repel each other, right? That means that the vector of charge B on P will point in that direction. And then how does sphere A and sphere P and point charge P interact? They attract each other. So A on P will be in that direction also. This will be electric field due to B, and this will be the electric field due to A. And let's move to 7.7. 7.7 says calculate the distance x between spheres A and B. So we are given the net electric field and the magnitude of the charges, right? And the distance between the point charge and one charge. So it should be obvious to see that we're going to use E net is equals to EB plus EA, right? So E net is 54.45 times 10 to the power of 4. And then the electric field due to B will be K. I won't substitute anything for K for the sake of space, right? And then the magnitude of B is 120 times 10 to the minus 9 divided by R squared, the distance between P and B, which is 0.05 squared. And then plus K again for the sake of space, the magnitude of A, 80 multiplied by 10 to the minus 9 divided by R squared. So R squared here will be the distance between A and P, right? Let's just put Y there. So let's put Y squared, right? So we are looking for X. You can see that X will be Y plus 0.05, right? So after we found Y, we basically have X. So if we do that, we can take this expression here to the left hand side, right? So we're gonna have 54,45 multiplied by 10 to the power 4 minus 9 times 10 to the power 9. I'm substituting K now, multiplied by 120 times 10 to the minus 9 divided by 0.05 squared. And then this will be equals to 9 times 10 to the power of 9 multiplied by 80 times 10 to the minus 9 divided by Y squared, right? So now I can rearrange this equation in attempt to find Y squared. So basically, if you have A is equals to B divided by Y and you want to find Y, you're going to cross multiply, get AY is equals to B, so Y will be B divided by C. You can see that B on our equation is this expression here, and then A on our equation is this entire expression, right? So let's rearrange it so that we can find Y ultimately. So we're gonna have Y squared is equals to 9 times 10 to the power of 9 multiplied by 80 times 10 to the minus 9 divided by this entire expression. So that's essentially what we're doing there. And then after this, we will take square roots on both sides. So we have Y squared to the power half, and then this entire expression to the power half. And then if you do that, you're gonna get Y is equals to 0.08 meters, right? So X will be 0.08 plus 0.05, which is 0.13 meters.